The most dangerous word in deep space may be back. Turn a spacecraft around. Point its nose toward the place you came from. Fire the engines for exactly as long as you did on the way out. It feels as though the path should reverse, as though distance were a line drawn across a dark floor and the ship could simply trace it home. But nothing is waiting where you left it. Earth has moved. The sun has moved. The solar system has carried both of them thousands of kilometers further through the galaxy, while your own spacecraft has continued along a different trajectory. Even the light reaching your windows is old. Every star you see is showing you where it was, not where it is. And the further you travel, the more deeply the sky becomes a record of vanished positions. This is the first thing deep space removes from human intuition, the belief that returning is merely departure played backward. On Earth, that belief usually works. You walk away from a house, turn around, and the door is still behind you. A road remains fixed beneath your feet. A mountain holds its shape against the horizon. Even an ocean crossing takes place inside a world dense with references. The sun rises. Stars arc across the sky. Currents carry patterns. Coastlines stay where charts say they should be. The environment moves, but not fast enough to destroy the meaning of direction. Deep space offers no such mercy. There is no road beneath the ship. No horizon divides one direction from another. No sensation tells the body that the craft has turned. If the engines are silent, a ship moving at thousands of kilometers per second feels exactly like a ship at rest. A cup floats beside a console. Dust drifts through a beam of instrument light. Outside, the stars appear still. Then the spacecraft rotates. The cabin turns. The stars slide across the windows. The engines ignite. Yet nothing in that movement proves the ship is going home. Rotation changes which way the vessel faces. Thrust changes its velocity. Neither action restores the trajectory it once followed. Because that old trajectory was not a tunnel left open in space. It was a sequence of positions occupied at particular moments, and every one of those moments is gone. In deep space, turning around changes where you face. It does not restore where you came from. To return, a spacecraft must do something far more difficult than reverse its motion. It must arrange a future encounter with a moving planet. That distinction is easy to miss, because everyday language treats destinations as places. We say Earth is here, Mars is there, and a nearby star lies 4 light-years away. But these are snapshots. They freeze a universe that does not pause. At this moment, Earth is rotating beneath your feet. At the equator, the surface moves at roughly 1,670 kilometers per hour. The planet travels around the Sun at nearly 30 kilometers each second. The Sun, carrying Earth with it, orbits the center of the Milky Way. Every second, the entire solar system enters a region of space it has never occupied before. Yet you do not feel any of this. Your house, the air, the ground, and your body share almost the same motion. Because everything nearby moves together, the world appears fixed. Home seems anchored. It is not anchored. It is carried. Imagine marking Earth's location with a luminous point, then watching for a year from somewhere outside the solar system. The point would not remain still. It would loop around the Sun. The Sun itself would move, turning that loop into a long spiral through the galaxy. Seen across enough time, Earth would not resemble a dot at all. It would become a thread, a continuous path through space and time. Physicists call such a path a world line. Your spacecraft has one. Earth has one. The Sun has one. Returning home means making the world line of the ship intersect Earth's world line again. Not where the planet was when you departed. Not where an old radio signal says it was. Where it will be when you arrive. That is already a more severe problem than aiming at a stationary target. A hunter can point toward a tree because the tree is expected to remain there. A spacecraft returning from interstellar distance must aim toward an absence. a region where Earth is predicted to appear years in the future. The prediction must each orbit around the Sun, the Sun's movement through the galaxy, the influence of the Moon and planets, the spacecraft's own velocity, every acceleration performed during the journey, every small force that has nudged it away from the path engineers intended. Some of those quantities can be known with extraordinary precision. Planetary motion is not random. Modern ephemerides can predict the positions of planets far into the future with remarkable accuracy. The laws of gravity do not suddenly become unreliable beyond Neptune. So the problem is not that Earth vanishes into chaos. The problem is that the returning ship must know enough about two moving paths, separated by an enormous distance and an enormous delay, to make them cross at the same point and at the same time. Miss the position, and you pass through empty space. Miss the time, and Earth crosses that region before or after you. A planet approximately 12,700 kilometers wide sounds like a large target. Across interstellar distances, it is almost nothing. More importantly, reaching the correct region is only the final step. Long before the planet can be seen as a world, the ship must already be following a trajectory accurate enough to enter the solar system at the right angle, at a survivable speed, with enough fuel left to correct whatever prediction was wrong. The geometry is unforgiving. A tiny angular error, preserved over trillions of kilometers, opens into a vast misdistance. A slight unmeasured acceleration can become a displacement larger than the space between planets. Not because the original error was dramatic, but because deep space gives every error time to grow. That growth does not announce itself. There is no moment when a warning light says the ship has become lost. The navigation display may continue showing a clean line towards Sol. The estimated position may remain precise to 6 decimal places, but every estimate contains uncertainty. A sensor has drifted by a fraction. A thruster produced slightly less force than commanded. A grain of dust struck the hull at extreme speed. A distant star's position was imperfectly known. At first, these differences are microscopic. Months later, they are kilometers. Years later, the spacecraft is no longer represented by a point. It occupies a widening region of possible positions, a cloud of uncertainty moving through the dark. You do not become lost all at once. Certainty leaks away. And once that leak begins, knowing where Earth will be is not enough. The ship must also determine where it is with a precision that no human traveller has ever needed before. That requires reference points, clocks, signals, and an unbroken chain of measurements reaching back to the moment of departure. But the deeper the ship travels, the older every signal becomes, the fainter every landmark appears, and the more the universe forces navigation to depend on imperfect evidence. To understand why home becomes so difficult to recover, we first have to abandon the idea that it is a point on a map. Home is a moving event, and the ship is already late. Late, because the word now has already split in two. There is the now inside the spacecraft, the present measured by its clocks, instruments, and crew. And there is the now on Earth, another present unfolding far away, carried by different motion, different gravity, and eventually, if the ship travels fast enough, a different rate of time. At first, those two moments seem connected. Messages still cross the distance. Mission control speaks. The crew replies. The delay is measured in seconds, then minutes, then hours. But once the spacecraft enters true interstellar space, the connection changes character. Earth is no longer something the crew experiences directly. It becomes something reconstructed from old signals and prediction. A transmission arrives showing oceans, weather systems, voices, elections, deaths, births. Yet every event in that signal happened before the light reached the ship. The farther away the ship travels, the farther into Earth's past it is forced to look. This creates a strange asymmetry. The travellers can calculate Earth's future position, but they can only see its past. They know where the planet should be according to orbital models. They can project the solar system forward through time, but the visible Earth, the radio Earth, the human Earth arriving through their antennas is always behind the equations. The map points forward. The evidence arrives backward. This is why a coordinate alone is never enough. A coordinate only has meaning inside a chosen reference frame and at a specified time. On Earth, coordinates feel permanent because the reference system is built around the planet. Latitude and longitude rotate with the surface. A city can keep the same address even while the entire planet moves around the sun because the grid moves with it. The address is not fixed in the universe, it is fixed relative to Earth. Astronomers use coordinate systems centered on Earth, the Sun, the solar system's center of mass, or the galaxy, depending on the problem. None is the universe's true map. There is no privileged grid engraved into space. Each is a mathematical choice designed to make a calculation manageable. Within the solar system, one useful reference is the barycenter, the common center of mass around which the Sun, planets, moons, and smaller bodies move. The Sun dominates the system, but it does not sit motionless at the center. Jupiter and the other planets tug on it. The solar system shifts around its own balance point. For navigation, that matters. If a returning spacecraft aimed at the place where a simplified diagram puts the Sun, it would be aiming at a symbol, not a physical prediction. Real navigation requires ephemerides, numerical models that calculate where celestial bodies will be at specific times. An ephemeris does not say, Earth is here. It says, within this reference frame, at this defined time, Earth is predicted to occupy this position and velocity, with this uncertainty. That last word matters. Uncertainty is not a confession of ignorance. It is part of the measurement itself. Every observed position has limits. Every mass estimate has error. Every model approximates forces too small or too numerous to calculate perfectly. The strength of modern navigation is not that it eliminates uncertainty, but that it measures uncertainty and carries it forward. A prediction without uncertainty is not precision. It is theatre. For nearby missions, the uncertainty can be extremely small. Engineers send spacecraft through narrow gravitational corridors, skim atmospheres, enter orbit, and strike asteroids hundreds of millions of kilometers away. These successes show that a moving solar system is not inherently unnavigable, but interstellar return stretches the same methods across a harsher scale. The farther into the future an ephemeris is projected, the more every small uncertainty has time to propagate. Earth's orbit is stable and constrained by centuries of observation. The major planets can be modelled far beyond the duration of any plausible near-future mission. Yet the spacecraft itself is not a planet following a stable orbit. It is a machine. It expels propellant, it sheds heat, it rotates. It experiences tiny imbalances in thrust. Its mass changes as fuel is consumed. Radiation pressure pushes against its surfaces. Gas trapped inside materials escapes. A small thermal asymmetry can produce a persistent force too weak for a body to feel, but strong enough to alter a trajectory over years. The Pioneer anomaly once appeared to be an unexplained acceleration affecting two distant probes. After years of analysis, the leading explanation was less exotic. Uneven heat radiation from the spacecraft produced a tiny recoil force. The effect was minute. The distance over which it acted made it measurable. That is the character of deep space navigation. The universe does not need to strike a ship violently to move it off course. It only needs to whisper for long enough. So engineers do not calculate one future path. They calculate a family of possible paths. At the center lies the best estimate. Around it lies a region describing where the spacecraft could plausibly be if measurements, forces, and models differ slightly from their assumed values. As new data arrives, that region can shrink. If contact is lost, sensors degrade, or external references become unreliable, it grows. The ship's world line becomes less like a single thread and more like a bundle of nearby possibilities. Earth has its own predicted world line. Returning means making these two bundles intersect. That is the real geometry of homecoming. Not a line drawn from a ship to a planet, not an arrow pointing toward a blue dot. A calculation asking whether two uncertain histories can be made to share one future event. And even that description hides another difficulty. The ship does not observe the universe from outside it. It is embedded in the same moving system it is trying to measure. Its cameras record angles from its own orientation. Its star trackers compare light against catalogues created from another location and epoch. Its accelerometers detect changes in motion but cannot reveal constant velocity. Its radio receives information delayed by distance. Every measurement is local. Every conclusion is inferred. This is why the question, "Where are we?" becomes increasingly difficult the farther the vessel travels. There is no single instrument that answers it. There is only a negotiation between predictions and evidence. A star tracker says the ship is oriented one way, an inertial unit says it rotated slightly farther. A radio range suggests the distance from Earth is larger than expected. A pulsar pulse arrives a fraction early. None of these readings is automatically the truth. Each carries noise, bias, and assumptions. Navigation software must decide which disagreement matters. Perhaps the star catalogue is outdated. Perhaps the clock has drifted. Perhaps a thruster underperformed months ago. Perhaps the ship is exactly where the instruments fear it is. Near Earth, mission control can test those possibilities quickly. Radar, optical observations, ground antennas, and known satellites provide dense layers of correction. In deep space, those layers thin out. The ship is not entering a region with no information. It is entering a region where every piece of information must carry more weight. And that weight is dangerous, because a reference can look stable long after its hidden errors have begun to grow. The traveller does not lose home because Earth ceases to exist. The traveller loses home when the chain connecting prediction to reality becomes too weak to trust. That chain begins with one question more fundamental than direction, distance, or speed. What in the sky can be treated as still? Almost nothing. The stars appear fixed because the human eye is poor at detecting the scale of their motion. Over one night, constellations rotate as a single pattern. Over one lifetime, most still look familiar. That apparent stability has guided navigation for centuries. But it is an illusion produced by distance. Every star is moving through the galaxy. Some drift toward us, some recede. Some cross the sky fast enough for their positions to change measurably within a few years. Barnard's star, one of the nearest stars to the Sun, shifts by more than 10 arc-seconds each year against the distant background. That is tiny to the naked eye, but enormous to a navigation system expected to remain accurate for decades. A star catalogue is therefore not a permanent map. It is a map stamped with a date. Astronomers record a star's position at a defined epoch, then measure its proper motion, the slow angular change caused by the star's true movement across our line of sight. To predict where it will appear later, software propagates that motion forward. For short missions, this works beautifully, but the farther into the future the calculation reaches, the more heavily it depends on the original measurement. A minuscule error may remain invisible for years, then become large enough to matter when a spacecraft is trying to determine its orientation far from Earth. Distance complicates the picture further. The position of a star in a camera is only a direction. It does not immediately reveal how far away the source is. Two stars can appear side by side, while one is 10 light-years away and the other is 10,000. The sky compresses depth into a flat surface. Astronomers recover some of that lost dimension through parallax. As Earth moves from one side of its orbit to the other, nearby stars appear to shift against more distant ones. A wider observing baseline improves the measurement. A spacecraft crossing the solar system can create an even larger one. In principle, an interstellar craft could use this to build its own three-dimensional map. In practice, the measurement becomes entangled with everything else the ship is trying to solve. To calculate parallax, the spacecraft must know how far it moved between observations. To know how far it moved, it must trust its velocity and timing. But those are the quantities the star observations are meant to correct. The ship uses the stars to estimate its motion, then uses its estimated motion to interpret the stars. This does not make navigation impossible. Modern estimation methods are designed for such loops. They combine uncertain measurements, compare predictions with observations, and continuously refine both the spacecraft's state and the environment around it. But the process depends on diversity. One kind of measurement cannot confirm itself forever. A star tracker may stabilize orientation. Radio ranging may constrain distance. Doppler measurements may constrain radial velocity. Pulsars may contribute timing and position from another geometry. Each method must challenge the others. Without that challenge, a navigation system can become confidently wrong. There is another reason the sky cannot be treated as a simple chart. Every point of light is old. Sunlight reaches Earth in a little over 8 minutes. The light from Sirius takes more than 8 years. The light from Betelgeuse began its journey centuries ago. A star on the far side of the Milky Way may be seen as it existed tens of thousands of years in the past. The spacecraft is not looking at one cosmic moment. It is looking at a mosaic of different ages. The nearest reference stars show relatively recent positions. The distant background shows older ones. A catalogue created on Earth predicts how these sources should appear from the solar system. But a ship far away observes them from another location and another time. The night sky is not the universe as it is. It is the universe arriving late. That delay does not usually prevent navigation, because astronomers model it. Apparent positions can be corrected for known motion, observer location, and light travel time. Yet every correction requires assumptions about distance and velocity. Errors in those assumptions feed into the predicted sky. For a slow spacecraft, the corrections remain manageable. For a craft moving at a substantial fraction of light speed, another transformation takes over. The direction from which light appears to arrive depends on the observer's velocity. This effect, called aberration, is already measurable from Earth. As our planet orbits the Sun, apparent star positions trace tiny annual shifts because Earth's velocity changes direction. At relativistic speed, the same principle becomes dramatic. Stars ahead of the spacecraft appear displaced toward the direction of travel. Stars behind shift away. As velocity increases, more of the visible sky seems compressed into the forward hemisphere. The pattern does not merely rotate, it changes shape. Color changes as well. Light from sources ahead shifts toward shorter wavelengths. Light from behind shifts toward longer ones. A familiar yellow star may appear bluer. Visible light may be pushed toward ultraviolet. Behind the ship, it may slide toward infrared. The sky becomes a velocity instrument, but only if the spacecraft understands the transformation well enough to decode it. Its own motion distorts the reference frame used to measure that motion. Yet relativity is not random. Aberration and Doppler shift follow precise equations. A capable computer can predict how a known star field should look at a given velocity, and compare that prediction with what the cameras detect. The danger lies in identification. A navigation system must determine which distorted point corresponds to which catalogued star. At high speed, position, color, and brightness can all change together. Radiation may blind detectors. Dust impacts may damage optics. Bright sources may saturate sensors, while dim references disappear into noise. A mistaken identification can poison every calculation that follows. If one star is assigned the wrong name, the software may infer the wrong orientation. If several false matches agree by coincidence, the system may settle on a coherent but incorrect solution. The display may show a precise position built on the wrong sky. This is why star trackers do not trust a single bright point. They recognize geometric patterns, angles between multiple stars, relative brightnesses, and repeated configurations. The pattern provides resilience if one source is obscured or misread. But patterns evolve. The farther the mission travels, the more its catalogue must be transformed, updated, and questioned. Nearby stars change perspective. Binary stars orbit. Variable stars brighten and fade. Some catalogue uncertainties are negligible near Earth, but significant after decades of extrapolation. The sky remains useful. It simply refuses to remain simple. This is the correction to the fantasy of a lost astronaut finding one familiar constellation and steering home. Constellations are views from one neighborhood. Leave that neighborhood far enough, the shapes deform. Travel fast enough, and your velocity deforms them again. Wait long enough, and the stars themselves move. A spacecraft can still navigate among them, but only by carrying a living model of the sky, rather than a frozen picture. And even a living model must be anchored to measurements. The spacecraft gathers fragments, an angle, a pulse, a frequency shift, a time delay. Each fragment constrains one part of the possible answer. Then, inside its computer, a cloud of possible positions is narrowed. Not to certainty, to the smallest region the evidence will allow. Near Earth, that region can be corrected constantly by a planet-sized system of antennas, clocks, and observers. Farther out, the spacecraft must depend increasingly on faint evidence crossing the dark. To understand how much confidence that evidence can buy, we have to see how spacecraft are actually found now, while Earth is still close enough to answer. While Earth is still close enough to answer, navigation is not a private act performed by the spacecraft alone. It is a conversation. A distant probe sends a signal. Giant antennas on Earth receive it. Engineers compare the time it left, the time it arrived, the frequency it carried, and the direction from which it came. From those fragments, they reconstruct the spacecraft's distance, velocity, and position. The word reconstruct matters. No antenna looks into the sky and sees a small machine floating against blackness. Most probes are far too dim, too distant, and too small for that. What mission control receives is often little more than a radio whisper, spread thin across millions or billions of kilometers. The signal may carry less power than the background noise around it. Still, the whisper is enough. NASA's Deep Space Network uses large antenna complexes in California, Spain, and Australia. Their separation around Earth allows at least one site to maintain contact as the planet rotates. Together, these stations form a tracking system large enough to follow spacecraft across the solar system. The most direct measurement is ranging. A coded radio signal is transmitted from Earth toward the spacecraft. The spacecraft receives it and sends a response. Engineers measure the total travel time. Because radio waves move at the speed of light in vacuum, that delay provides a distance along the line between Earth and the probe. The calculation sounds simple. It is not. The signal does not leave from a motionless Earth. The tracking antenna is rotating with the planet. Earth is orbiting the Sun. The spacecraft is moving. Gravity bends trajectories and alters clock rates. Plasma in the solar wind can delay radio waves. Equipment introduces its own internal delays. Every one of these effects must be modelled. Then comes Doppler tracking. If the spacecraft moves away, the received radio frequency is stretched lower. If it moves toward Earth, it is compressed higher. By measuring that shift with extraordinary precision, engineers determine the spacecraft's velocity along the line of sight. Distance tells them where the spacecraft lies along one direction. Doppler tells them how that distance is changing. But neither measurement alone fully fixes a position in 3 dimensions. A spacecraft can occupy many possible points at roughly the same range from Earth. Engineers need angular information as well. One method uses widely separated radio antennas to listen to the same spacecraft signal. Because the antennas occupy different positions on Earth, the wave reaches each one at a slightly different time. That tiny difference constrains the signal's direction in the sky. For especially precise work, the spacecraft's signal can be compared with radio waves from distant quasars. Quasars are active galactic nuclei, so remote that their apparent directions remain exceptionally stable for navigation purposes. By observing the spacecraft and a nearby quasar, engineers reduce errors caused by Earth's atmosphere and the geometry of the tracking network. Distance, radial velocity, direction. No single measurement gives the answer. Together, they begin to close around it. The process resembles tightening several invisible cords around a point in darkness. One measurement rules out a vast region, another rules out more. A third leaves a smaller volume where the spacecraft can plausibly be. Then physics carries that estimate forward. Mission software predicts how gravity should move the spacecraft from one moment to the next. The Sun dominates much of the motion. Planets add smaller perturbations. Thruster burns alter velocity deliberately. Radiation pressure and thermal forces contribute faint but measurable pushes. A predicted trajectory emerges. When the next observation arrives, engineers compare it with the prediction. If the radio signal returns slightly later than expected, the spacecraft may be farther away. If the Doppler shift differs, its velocity may be wrong. If the angular measurement places it to one side, the trajectory may need to be revised. The difference between prediction and observation is called a residual. Residuals are where the truth begins to press against the model. A small residual may be ordinary noise. A pattern of residuals may reveal a systematic error, an incorrect estimate of a planetary mass, an unmodelled force, a clock offset, or a thruster burn that produced slightly different motion than commanded. Navigation teams do not ask whether the model is perfect. They ask how it is wrong. That habit is one of the quiet achievements behind modern spaceflight. Spacecraft reach distant worlds not because their original trajectories remain flawless, but because errors are detected before they become fatal. A mission may launch with an excellent course and still perform several trajectory correction maneuvers. Each burn adjusts velocity by a small amount. The change may seem negligible, but applied early enough, it shifts the spacecraft's future position by thousands of kilometers. A tiny correction now can prevent an enormous miss later. That principle guided New Horizons toward Pluto. It guided probes through narrow windows near Jupiter and Saturn. It allows spacecraft to enter orbit around planets that are themselves moving rapidly when the vehicle arrives. The popular image of spaceflight is a machine following a line. The real image is a machine followed by uncertainty, repeatedly measured and repeatedly corrected. Even Voyager, travelling far beyond the planets, remains connected to this process. Earth receives its faint transmission, estimates its state, and updates predictions of where it will be. The spacecraft is distant, but not abandoned to pure dead reckoning. This matters because it reveals what present-day deep space navigation truly depends on. Not only onboard intelligence, not only stars, infrastructure, a network of atomic clocks, precisely surveyed antenna locations, planetary ephemerides, atmospheric models, engineers monitoring residuals, software carrying uncertainty forward, decades of accumulated observations. The spacecraft may be alone in the image, but the act of knowing where it is belongs to an entire civilization. Remove that civilization from the loop, and the spacecraft does not instantly become blind. It still has gyroscopes, accelerometers, cameras, clocks, and stored models. It can continue propagating its estimated state. But the corrections become rarer. The uncertainty begins to widen. At interstellar distances, the deep space network could still receive and transmit signals in principle if the spacecraft carried sufficient power and Earth had sufficiently sensitive antennas. The fundamental obstacle is not that radio suddenly stops at the edge of the solar system. It is that distance attacks the usefulness of the exchange in two ways at once. The signal weakens, and the answer arrives late. Double the distance, and an unfocused signal spreads across roughly 4 times the area. The receiving antenna captures a smaller fraction. Increase the distance by thousands, and the transmitter must become vastly more powerful, the antenna vastly larger, the data rate vastly lower, or all three. A message may still cross the void, but it crosses as a whisper that took years to arrive. Mission Control could calculate a correction using the spacecraft's reported position. By the time the instruction reached the ship, that position would belong to the past. The craft would have travelled onward, accumulating new errors that Earth had not yet seen. The loop that works so well within the solar system stretches open. Observation, calculation, command, response. Each step is separated by years. At that point, Earth can still contribute knowledge, but it can no longer function as the spacecraft's nervous system. The ship must begin making navigational judgments for itself. And that means carrying forward the one weakness Earth-based tracking has been quietly correcting all along. Every internal measurement drifts. A gyroscope does not know where the stars are. An accelerometer does not know where Earth is. These instruments only measure changes occurring inside the spacecraft: rotation, acceleration, vibration, the slight push of an engine, the recoil of a mechanism, the tremor of a collision too small for any human body to notice. If the ship begins with an accurately known position and velocity, then in principle every later position can be calculated by integrating those changes over time. This is inertial navigation. It is one of the purest ideas in wayfinding. Know where you started, measure every motion afterward, and the path should remain recoverable without looking outside. Aircraft use it, submarines use it, missiles use it, spacecraft use it, and every inertial system eventually becomes wrong. The failure does not begin with a dramatic malfunction. It begins with bias. An accelerometer sitting perfectly still may report an acceleration that is not exactly zero. The error can be microscopic, perhaps smaller than anything visible on an ordinary display. But navigation software treats the reading as real unless another measurement corrects it. That false acceleration becomes false velocity. False velocity becomes false distance. Because the calculation is integrated over time, the error does not merely remain, it grows. A constant acceleration bias produces a position error that increases with the square of time. Leave it uncorrected long enough, and a measurement too small to matter during launch can become the reason a spacecraft arrives millions of kilometers from where it believes itself to be. Gyroscopes create a related danger. A gyroscope tells the spacecraft how it is oriented, but every real gyroscope has drift. Temperature changes its behavior. Radiation alters electronics. Mechanical stresses shift alignments. Tiny manufacturing imperfections produce small rotational errors. If the spacecraft thinks its nose is pointing one direction when it is actually pointing another, every engine burn is applied along the wrong line. The thruster may fire for exactly the correct duration. The spacecraft may gain exactly the commanded amount of speed, and the trajectory may still be wrong because the direction was wrong by a fraction of a degree. Over short distances, that fraction can be corrected. Across light years, geometry gives it time to open. This is why early spacecraft did not rely on inertial guidance alone. Apollo carried a guidance platform, but astronauts also performed star sightings. They aligned an onboard optical instrument with known stars and used those observations to correct accumulated drift. The inertial system carried the trajectory between sightings. The sky repaired the inertial system. True interstellar travel would demand the same relationship for years or decades under conditions no instrument has yet survived. The spacecraft would need to know not only whether a sensor had changed, but whether the change belonged to the ship, the instrument, or the environment. A slight rotation might be a genuine torque from a dust impact. It might be thermal deformation. It might be a gyroscope slowly lying. The data alone does not announce which explanation is correct. That is why uncertainty must be propagated alongside the estimate. Suppose the navigation computer believes the craft is at one point in space. It also carries a mathematical description of how uncertain that belief is in every direction. Perhaps the position is known more accurately along one axis than another. Perhaps velocity uncertainty dominates. Perhaps orientation uncertainty threatens the next maneuver. This evolving structure is often represented through a covariance matrix, though the mathematics is less important than the meaning. The spacecraft is not a dot. It is a probability cloud. Every uncorrected second lets that cloud deform and expand. Some uncertainties grow slowly, others couple together. An orientation error affects thrust direction. A thrust error affects velocity. A velocity error affects future position. A clock error corrupts range measurements. One weakness feeds another. Deep space does not create these errors. It removes the nearby references that keep them small. On Earth, an aircraft's inertial system can be corrected using satellites, radar, terrain, or radio navigation. The submarine may surface or use external fixes. A spacecraft near Earth can compare its internal estimate with ground tracking and optical observations. Far between stars, there may be long intervals during which nothing provides a clean, independent correction. Then dead reckoning becomes dangerous not because it is useless, but because it can remain plausible while drifting away from reality. The navigation display may show a trajectory with exquisite precision. The numbers can be stable. The predicted arrival can be calculated down to the second. Precision on a screen does not guarantee accuracy in space. A computer can report the wrong answer with perfect confidence if its inputs have drifted together. Consider a single thruster pulse. Mission software commands a burn intended to change velocity by a tiny amount. The valve opens. Propellant flows. Hot gas expands through the nozzle. The spacecraft responds. But the thrust is never an abstract vector. Its force depends on pressure, temperature, fuel mixture, valve timing, nozzle condition, and the changing mass of the spacecraft. The nozzle may not point exactly through the center of mass. The burn may introduce a slight rotation. Fuel may slosh. A neighboring surface may reflect exhaust unevenly. Engineers characterize these effects carefully. For missions lasting years, they can estimate performance with astonishing skill. Yet interstellar navigation asks those estimates to remain trustworthy over a duration longer than the operational life of any spacecraft ever built. Components age. Calibration shifts. Redundant systems fail one at a time. The instrument used to correct another instrument may itself be drifting. Even heat becomes a navigational force. A spacecraft radiates energy in all directions, but rarely with perfect symmetry. If one side emits slightly more thermal radiation than another, photons carry momentum away unevenly, producing a faint recoil. The force is nearly nothing. Nearly nothing, applied continuously, is one of the most powerful agents in deep space. The same is true of starlight. Photons striking the spacecraft exert pressure. Gas leaks from materials. Radio transmissions produce recoil. A reaction wheel changes speed. A mechanical arm moves. Each event alters momentum, usually by an amount too small to matter immediately. But interstellar navigation is the science of refusing to dismiss small things merely because they are small. Time promotes them. A speck of dust striking at high relative velocity may chip shielding or impart a tiny impulse. A larger grain could damage optics or force the ship into an emergency maneuver. Cosmic radiation may flip bits in memory, degrade detectors, and slowly shift sensor response. None of this guarantees failure. A robust spacecraft can carry shielding, redundant sensors, self-calibration routines, autonomous diagnostics, and spare components. Future quantum inertial sensors may reduce drift dramatically. Cold atom interferometers could measure acceleration and rotation with sensitivity far beyond many conventional devices. But greater precision does not abolish the need for correction. It only delays the moment when uncertainty becomes operationally dangerous. This is the central cruelty of dead reckoning across interstellar distance. The method becomes most necessary exactly where its weaknesses have the longest time to accumulate. The ship can measure itself with extraordinary care. It can remember every burn. It can model every known force. It can still be moved by something it failed to measure. And because space contains no roadside marker announcing the mistake, the first clear evidence may arrive only when an expected star is slightly displaced. A pulsar pulse arrives too early, or the signal from Earth appears from an angle that the ship's model cannot explain. By then, the error has already become distance. The next question is whether a message from home can shrink that distance before it grows again. It can, but never immediately. A radio correction from Earth is not a hand reaching across space. It is a piece of information travelling at the fastest speed the universe permits, and even that speed becomes painfully slow once the distance is measured in light years. Close to Earth, the delay is almost invisible. Signals between the ground and low orbit take only fractions of a second. A controller can notice a problem, send a command, and watch the result almost in real time. At the Moon, the conversation already changes. A signal takes a little more than a second to cross the distance one way. At Mars, depending on the positions of the two planets, the delay can range from several minutes to more than 20 minutes. A rover cannot be driven like a remote-controlled car. Instructions must be planned, transmitted, executed, and reviewed after the fact. Voyager operates under an even harsher rhythm. A signal requires many hours to travel from Earth to the spacecraft. A complete exchange takes more than a day. Mission control can still guide it because the spacecraft moves slowly by interstellar standards, and because most decisions do not require instant response. Now extend that delay to another star. From 4 light-years away, a message sent toward Earth takes 4 years to arrive. The reply takes 4 more years to return. One question creates an 8-year silence. During those 8 years, the spacecraft continues moving. Its instruments age. Its position uncertainty expands. A thruster may underperform. A sensor may fail. A collision may alter its orientation. By the time Earth receives the original report, calculates a correction, and sends instructions back, the spacecraft described in the report no longer exists in that state. Mission control would be solving a historical problem. The ship would be living inside a new one. At interstellar distance, mission control does not tell you where you are. It tells you where you were. This does not make communication worthless. Earth can still transmit updated star catalogues, pulsar timing models, software patches, predictions of the solar system's future position, and advice based on long-term trends. It can help the spacecraft improve its understanding of the environment. What Earth cannot do is close the control loop quickly enough to steer around immediate danger or correct a rapidly developing navigational error. The ship must decide first. Earth can judge later. Signal strength adds another constraint. Radio energy spreads as it travels. A narrow beam can concentrate much of that energy in one direction. But no real transmitter produces an infinitely thin ray. The beam widens. Its power is distributed over an ever larger area. By the time a signal crosses interstellar distance, only a tiny fraction may strike a receiving antenna. The inverse square law is unforgiving. Increase distance by a factor of 10, and the same transmitted power is spread over roughly 100 times the area. Increase distance by 1,000, and the received intensity falls by roughly 1,000,000. This does not mean interstellar communication is impossible. Large antennas, high transmitter power, narrow laser beams, long integration times, and advanced error correction can recover signals that seem impossibly faint. But communication becomes slower in another sense. A weak signal carries less usable information per unit time. The receiver may need to listen for minutes, hours, or days to distinguish a message from noise. Data rates fall. A detailed image may take months to transmit. A navigation update may need repeated confirmation before the spacecraft trusts it. The universe does not silence the signal completely. It thins the conversation until every bit becomes expensive. Lasers offer advantages because shorter wavelengths can be focused into narrower beams than ordinary radio transmissions. A precisely aimed optical link could deliver higher data rates across enormous distances. Yet precision creates fragility. The transmitter must point toward where the receiver will be when the beam arrives, not where it was when the light left. A tiny aiming error at the source becomes an enormous miss at the destination. The receiving spacecraft must know when and where to look. Dust, pointing jitter, detector noise, and the motion of both endpoints complicate the exchange. The act of sending navigation data becomes a navigation problem of its own. And even a perfect beam still travels at light speed. No antenna, laser, computer, or future engineering breakthrough can make the news arrive before causality allows it. This forces a fundamental change in how an interstellar spacecraft must be designed. It cannot be a distant machine waiting for instructions. It must become an autonomous observer, navigator, and decision maker. Onboard software would combine inertial measurements, star fields, pulsar pulses, thermal models, propulsion data, and every available signal from Earth. It would estimate not only where the ship is, but how much trust each instrument deserves. If one star tracker disagreed with the inertial system, the software would need to determine whether the camera had misidentified the sky, the gyroscope had drifted, or the spacecraft had experienced an unmeasured torque. If a pulsar pulse arrived earlier than predicted, the system would ask whether its position was wrong, its clock was wrong, or the pulsar model was incomplete. The computer would not simply calculate, it would diagnose. That requires more than intelligence in the ordinary sense. It requires caution. A navigation system that reacts aggressively to every anomalous reading may waste fuel chasing noise. A system that reacts too slowly may allow a real error to grow beyond recovery. Every course correction becomes a wager. Burn propellant now, and the ship may reduce an error that was never real. Wait for more evidence, and a real deviation may become too large to correct efficiently. Near-Earth engineers can debate that choice with fresh data and human judgment. Between stars, the spacecraft may have to make it alone, knowing that Earth will not learn what happened for years. This loneliness is not merely emotional, it is operational. The craft must carry enough redundancy to survive contradictory evidence. Multiple clocks, multiple star trackers, independent inertial systems, separate navigation computers using different software, sensors capable of cross-checking one another rather than failing in the same way. Redundancy matters because identical systems can share identical mistakes. Two sensors built from the same design may drift together. Two programs based on the same model may agree because both emit the same force. Agreement is useful only when the methods are genuinely independent. Deep space navigation depends on disciplined disagreement between imperfect instruments. That disagreement is what prevents one quiet error from becoming reality inside the computer. The spacecraft may also use delayed messages from Earth as anchors. Even an 8-year-old correction can reveal whether the onboard estimate had been drifting systematically. By comparing what Earth believed years earlier with what the ship recorded at the time, the software can recalibrate parts of its history and improve future predictions. But the correction cannot undo the motion already completed. It can only change what happens next. This is the irreversible structure of navigation across light years. Information arrives after the event it describes. Decisions must be made before outside confirmation. Every response belongs to a version of the ship that has already moved on. The farther the traveller goes, the more Earth becomes an archive rather than a guide. Its signals remain precious. They carry updated knowledge, human voices, evidence that the planet still exists. But they no longer form a hand on the controls. The ship must navigate by a sky distorted by its own motion, by instruments that slowly drift, and by messages that become older with every kilometre. And if it moves fast enough to cross the distance within a human lifetime, even the appearance of that sky will begin to change. At first, the change would be subtle. The stars ahead would shift by fractions of a degree. Colours would move slightly. Familiar patterns would remain recognisable, though no longer exact. A navigation computer could correct for the distortion with little difficulty. But as the spacecraft approached a significant fraction of the speed of light, the sky would stop behaving like a passive background. It would begin responding to the motion of the observer. This is not an optical illusion in the ordinary sense. The light reaching the ship is real. What changes is the angle and frequency at which that light arrives because the spacecraft is moving so quickly through the incoming radiation. The effect is called relativistic aberration. A useful comparison is rain striking the windshield of a moving car. To someone standing still, the rain may fall vertically. To the driver, the drops appear to slant toward the front because the car is moving into them. The faster the car travels, the more sharply the rain seems to approach from ahead. Light behaves differently from rain, but the geometry carries the same intuition. As the spacecraft accelerates, photons that would have entered from the side appear to come from farther forward. Sources spread across the sky are displaced toward the direction of travel. The forward field becomes crowded. The rear field opens and thins. At extreme speed, much of the visible universe appears compressed into a bright region ahead. The ship has not pulled the stars together. Its motion has changed the directions from which their light enters. This matters immediately for navigation. A star tracker built around a catalogue of expected angular positions can no longer compare the raw image with the map. Every point must first be transformed according to the spacecraft's estimated velocity. But the estimated velocity is one of the quantities the stars are supposed to help determine. Again, the instrument and the model depend on each other. The computer predicts how the sky should look at a given speed. It compares that prediction with the observed image. It adjusts the speed, orientation, and position estimate until the transformed catalogue aligns with the detected pattern. When the match is good, confidence increases. When it is not, the disagreement could mean several different things. The ship may be moving faster than expected. Its orientation may be wrong. The camera may be misaligned. A star may have been misidentified. The catalogue may have propagated an old position incorrectly. The sky does not offer one clean answer. It offers a set of constraints that must agree. Frequency shifts add another layer. A spacecraft moving toward a light source measures that light at a higher frequency. Moving away shifts it lower. In visible light, the effect is described as blue shift ahead and red shift behind. Though at sufficient speed, the changes extend far beyond visible color. Infrared radiation from the forward direction can be shifted into visible wavelengths. Visible starlight may be pushed into ultraviolet. Ultraviolet can move into X-rays. Behind the ship, familiar light can slide toward red, then infrared, becoming invisible to ordinary cameras. The stars do not merely change color. Some disappear from one detector and emerge in another. A navigation system designed for relativistic flight would need instruments covering a broad range of wavelengths. It could not trust a visible light star field alone, because speed itself would move reference signals across the spectrum. Brightness changes too. Photons arriving from ahead are not only shifted in frequency, their energy increases in the spacecraft's frame, and their arrival directions are concentrated. The forward sky brightens through relativistic beaming. Behind, the sky dims. The visual result would be severe. Ahead, a compressed cone of intensified radiation. Behind, a stretched and fading darkness. The faster you travel, the less the sky resembles the map that launched you. Yet none of this is unknowable. Relativity provides precise transformations. If the spacecraft knows its velocity, it can predict the distorted sky. If it observes the distorted sky accurately, it can infer aspects of its velocity. The same effect that destroys the usefulness of an uncorrected star chart becomes a source of navigational information. But this only works while the instruments remain within their designed limits. A camera can saturate when a source becomes too bright. A detector can be blinded by radiation shifted into more energetic bands. Protective shielding may block wavelengths the navigation system suddenly needs. A star used as a reliable reference may be drowned in the forward glare or shifted outside the instrument's sensitivity. Even empty space becomes more dangerous in the forward direction. The thin gas and dust between stars is sparse enough to qualify as an excellent vacuum by earthly standards. At relativistic velocity, however, each particle strikes with enormous kinetic energy. Individual hydrogen atoms become a stream of high-energy radiation in the spacecraft's frame. Dust grains become microscopic projectiles. A shield built to absorb those impacts may heat, erode, and emit radiation of its own. That glow can contaminate sensors facing forward, precisely where the star field is most compressed and most useful for determining the direction of travel. Navigation and survival begin competing for the same view. The safest side of the ship to hide instruments may be the worst side from which to observe. The forward shield protects the spacecraft, but it also blocks the sky. Engineers could place sensors on articulated structures or use mirrors and indirect optical paths. They could observe stars away from the most dangerous axis. They could pause major measurements during periods of acceleration, or use pulsars detected in X-rays from safer angles. Every solution adds machinery. Every mechanism adds failure modes. At lower speeds, a human looking through a window might still recognize constellations after some adjustment. At higher speeds, instinct becomes nearly useless. The eye expects the sky to be a stable sphere surrounding the observer. Relativistic motion turns it into a velocity-dependent projection. There is no natural horizon, no bodily sense of forward motion, no wind, vibration, or passing landscape. Only a sky whose shape has become inseparable from the speed of the ship. A traveller could look ahead and see stars crowded into brightness, then turn toward the rear and find a darker, redder field. The visual system would interpret this as a landscape, but it would not be a landscape. It would be the mathematical consequence of motion. The ship is carrying its own distortion with it. This makes a simple phrase like "point toward Earth" far more demanding than it sounds. Earth's light would also be aberrated, shifted, delayed, and faint. The sun might be identifiable by spectrum, pulsar relative geometry, or a precisely transformed catalogue, but not by searching for the familiar yellow point remembered from departure. The faster the ship travels, the more carefully it must subtract itself from everything it sees. Its velocity is written across the sky. Its uncertainty is written there too. And once the spacecraft moves fast enough for these effects to become dramatic, another assumption fails beneath them. The problem is no longer only where Earth will be. It is what the word now means at both ends of the journey. It means less than it did before departure. On Earth, now feels universal. You look across a room and assume every object exists in the same present. You call someone in another city and accept that, apart from a slight transmission delay, both of you inhabit the same moment. That intuition survives because the distances are small and the relative speeds are slow. Across light years, it fails. Special relativity does not allow a single universal present shared by every observer. Two people moving differently can disagree about whether distant events happened at the same time, and neither observer is mistaken. This is the relativity of simultaneity. It is not a problem caused by bad clocks. It remains even if every clock is perfect. It is not a delay that better technology can remove. It is built into the geometry of space-time. Imagine two flashes occurring far apart. An observer positioned between them receives both flashes at the same moment and concludes that the events were simultaneous. Another observer moving toward one flash and away from the other receives the light differently. After correcting for the travel time of the signals, that observer can still assign the events a different temporal order because their frame divides space-time into nows along a different angle. No experiment can reveal which observer possesses the universe's true present. There is no true present to find. For a spacecraft returning from another star, this changes the meaning of Earth's current position. The ship can choose a reference frame and calculate where Earth is at a particular coordinate time. Engineers can define a solar system frame, propagate planetary ephemerides, and predict the planet's motion with precision. Navigation remains possible, but the phrase, "where Earth is right now," is incomplete until the frame and the meaning of now are specified. The answer from Earth's frame is not identical to the answer assigned by a rapidly moving spacecraft. This does not cause the planet to blur into multiple physical locations. Earth follows one continuous world line. The disagreement concerns which distant event on that world line should be called simultaneous with the ship's present event. Think again of the two threads, one traced by Earth, one by the spacecraft. At each point on the ship's world line, its reference frame draws a surface through space-time representing distant events it labels as occurring now. Change the ship's velocity, and that surface tilts. When the spacecraft turns around, its definition of distant simultaneity changes. The reversal is not merely a mechanical maneuver, it changes which event on Earth's world line the traveller regards as happening at the same time as the turn. This is one reason the famous travelling twin problem feels so unsettling. The traveller departs, accelerates, turns around, and returns younger than the person who remained on Earth. There is no contradiction because the two twins follow different paths through space-time. The traveller changes inertial frames during the turnaround, while the Earth-bound twin approximately remains in one frame for the simplified argument. The age difference is real. Atomic clocks carried on aircraft and satellites have measured smaller versions of the same effect. Modern satellite navigation systems must correct for relativistic differences in clock rates. Relativity is not an exotic decoration added to interstellar travel. It already operates inside the technology people use to find a street address. At interstellar speed, the correction becomes the architecture of the journey. Suppose the spacecraft travels at 90% of the speed of light relative to Earth. Its Lorentz factor is a little over 2. For a long coasting segment, roughly 2 years can pass on Earth for each year measured aboard the ship. At 99% of light speed, the factor rises above 7. The crew's watches do not appear slow to them. Hearts beat normally. Food cools normally. Thoughts take their ordinary time. Inside the cabin, physics behaves as it always has. It is Earth that ages faster relative to their journey. A message from home may report years of history that the crew has not personally lived through. Children become adults between exchanges. Institutions change. People who promise to wait may reach old age while the traveller remains comparatively young. This is not because the signal exaggerates the passage of time. The time has passed. The traveller simply experienced less of it. At this point, the navigational problem changes its emotional shape. Until now, the danger has been missing Earth in space. Relativity reveals another possibility: arriving at the correct planet in the wrong human era. A perfect ephemeris can predict where Earth will be. It cannot preserve what Earth will be. The spacecraft may cross the final astronomical units with flawless accuracy. The Sun may appear exactly where the models predicted. The planets may match their calculated positions. Radio beacons may guide the ship toward a planned rendezvous. And still, everything that made the departure meaningful may belong to the past. This is the midpoint, hidden inside the question of finding home. Position was never the deepest problem. Time was. A traveller does not leave Earth alone. The traveller leaves a specific Earth, one arrangement of people, languages, cities, memories, and unfinished conversations. That arrangement is not carried along with the ship. It continues changing on its own world line. Even without relativistic speed, distance creates delay. A traveller 4 light years away sees Earth 4 years in the past. At high speed, time dilation widens the separation further. The ship receives a delayed image of a world that is also aging faster relative to the traveller. The crew lives between 2 Earths. One is the remembered Earth at departure. The other is the predicted Earth of arrival. Neither is fully visible. The first survives in recordings and memory. The second exists only in models and messages from earlier stages of its history. Home becomes a hypothesis about the future. This is why the return journey cannot be understood as reversing a route. Reversal suggests restoration. It suggests that every kilometre recovered brings the traveller closer to the same condition that existed before. But the distance closes while the temporal separation remains. The ship can reduce the number of kilometres between itself and Earth. It cannot reduce the number of years that Earth has already lived. No engine points backward through proper time. No navigation system calculates a course into an earlier event. The universe does not contain a hidden road leading to the morning of departure. Once an event has passed, its coordinates remain in space-time, but they are not a destination a slower-than-light traveller can revisit. The world line moves forward. The ship can intersect it again only at a later point. That later point may still be home in every legal and astronomical sense. It may still contain the same oceans, continents, and species. It may welcome the traveller with signals prepared decades before. But it will not be the event that was left behind. The distinction is severe because it survives every engineering success. Build perfect gyroscopes. Map every star. Detect every pulsar. Transmit with flawless lasers. Predict Earth's orbit without error. The temporal loss remains. Technology may solve the problem of reunion. It cannot turn reunion into return. And now the next instrument becomes essential, because if the spacecraft is to meet Earth's future world line at all, it needs clocks more stable than memory and reference signals that remain recognizable when ordinary stars have shifted. For that, engineers look toward the remnants of dead suns, spinning in the dark with the regularity of cosmic machinery. A pulsar is what remains when a massive star dies badly. After the star's core collapses, matter is compressed so violently that protons and electrons are driven together. The result is a neutron star, an object with more mass than the Sun, packed into a sphere roughly the size of a city. Some neutron stars rotate. Some rotate hundreds of times each second. Their magnetic fields channel radiation into narrow beams that sweep across space. If one of those beams crosses Earth, or a spacecraft, the source appears to pulse with each rotation. The pulse is not the star switching on and off. It is a lighthouse effect produced by geometry. Millisecond pulsars are especially valuable because their rotation can remain extraordinarily stable over long periods. They are not perfect clocks, but some rival the long-term regularity of human atomic timekeeping. That suggests a navigational system. A spacecraft carries an instrument capable of detecting X-rays from several known pulsars. It measures exactly when each pulse arrives. Because the expected pulse pattern at a reference location has been predicted in advance, any delay or advance contains information about the spacecraft's position. If a pulse arrives earlier than expected, the spacecraft may be closer to that pulsar along the relevant line of sight. If it arrives later, the craft may be farther away. One pulsar constrains position along one broad direction. Several pulsars distributed across the sky allow the navigation computer to solve for a three-dimensional position and correct its clock at the same time. The principle resembles GPS, only from a distance. GPS satellites broadcast carefully synchronized time signals from known locations near Earth. A receiver compares arrival times and solves for its own position. Pulsars do not cooperate. They are not arranged for us. They do not transmit coded timestamps. They are thousands of light years away, faint, irregular in detail, and embedded in backgrounds of radiation. A spacecraft must know their timing models, account for the motion of the solar system, correct for relativity, and gather enough photons to distinguish real pulses from noise. Still, the idea works. An experiment aboard the International Space Station used X-ray signals from millisecond pulsars to estimate the station's position without relying on ordinary satellite navigation. The result was accurate to within several kilometers. For an instrument listening to dead stars across the galaxy, that is remarkable. It proves that nature contains enough structure for a spacecraft to navigate without asking Earth where it is. But the success can be misunderstood. A pulsar navigation system does not reveal an absolute position in the universe. It estimates position inside a chosen reference frame, using pulsars whose directions and timing behavior have already been modeled. The coordinates remain relational. The map is still built from moving things. Pulsars themselves change. They lose rotational energy and slow over time. The effect is often predictable, allowing timing models to project pulse arrival far into the future. But some pulsars experience timing noise. Others undergo glitches, sudden small changes in rotation caused by processes inside the neutron star. A glitch is tiny in physical terms. For a navigation system depending on precise pulse phase, it matters. If Earth observes the change, updated timing parameters can eventually be transmitted to the spacecraft. But the message may take years to arrive. Until then, the ship must determine whether an unexpected pulse belongs to its own position error, its onboard clock, or the pulsar. The clock used to correct the spacecraft has become another object requiring diagnosis. Detection is equally demanding. X-ray pulsars are faint. A detector does not receive a clean mechanical tick. It records individual high-energy photons arriving against instrumental noise and diffuse cosmic backgrounds. The navigation computer folds those arrival times over the expected pulse period, accumulating evidence until a pattern emerges. This takes time. A brighter pulsar may produce a usable estimate relatively quickly. A fainter one may require long observation. During that interval, the spacecraft continues moving, perhaps rapidly. Its orientation may change. Vibrations may affect the detector. Radiation may alter sensitivity. Navigation is no longer a matter of looking once and reading a number. It is the slow construction of confidence from sparse events, photon by photon. The ship argues with the dark. A practical system would likely observe several pulsars repeatedly rather than continuously. It would combine those measurements with inertial navigation and star tracking. Between pulsar fixes, the spacecraft would propagate its state forward. When new timing data became available, it would update the estimate and reduce accumulated drift. This makes pulsars powerful because they fail differently from gyroscopes. An inertial sensor drifts internally. A star tracker depends on angular patterns. A radio signal depends on contact with Earth. A pulsar provides a timing reference, generated far beyond the spacecraft, unaffected by the aging hardware aboard it. When independent systems agree, the ship gains confidence. When they disagree, the disagreement becomes evidence. But pulsar navigation also inherits the relativistic problem already transforming the visible sky. The pulse frequency observed by the spacecraft depends on its motion relative to the source. If the craft is moving toward a pulsar, pulses arrive more rapidly. If it is moving away, they arrive more slowly. The system must separate changes caused by position from changes caused by velocity. Its onboard clock also matters. If the clock drifts, every pulsar appears wrong in a related way. With enough sources, the navigation solution can estimate clock error alongside position, but only if the timing models and detector data are strong enough. There is no single, clean tick that announces home. There is a network of faint, delayed, velocity-shifted rhythms that must be solved together. And even the word delayed carries a subtle danger. The pulses reaching the spacecraft were emitted centuries or millennia earlier, depending on the source distance. Yet this does not make them useless. Their timing patterns are predictable because the rotational behavior has been modeled. A navigator does not need to know what the pulsar is doing now in some universal sense. It needs to predict the phase of the radiation arriving here. That distinction is crucial. Navigation depends on what can affect the spacecraft, not on inaccessible events occurring elsewhere at the same imagined cosmic present. In this way, pulsars offer something close to a natural coordinate lattice. Not fixed points, not perfect clocks, but distant references stable enough to reduce uncertainty when ordinary Earth-based guidance has become too slow. Future spacecraft might carry larger X-ray detectors, more precise atomic clocks, and software capable of updating pulsar models autonomously. They might identify timing glitches by comparing many sources. They might use pulsars to cross-check optical navigation and inertial estimates over decades. Such a system could make interstellar navigation practical. It could help a traveler calculate a path back toward the solar system. It could tell the ship that its internal estimate has wandered. What it cannot do is recover the Earth that existed when the ship departed. The pulsars can mark where the spacecraft is. They can help predict where Earth will be. They cannot make the two clocks share the years between them. This is why the same technology carries both hope and warning. The galaxy may provide reference signals strong enough to guide a ship through interstellar space. But every signal is also a reminder that navigation is built from time. Position is extracted from timing. Distance is inferred from delay. Velocity is written into frequency. And a return address is meaningful only if it includes not just where, but when. That is precisely what humanity tried to engrave onto the first objects we knowingly sent toward the stars. On the cover of each Voyager Golden Record, a small diagram attempts something almost impossible. It tries to tell a stranger where we are. The diagram does not use kilometers. It does not name Earth. It does not assume that whoever finds the spacecraft knows our language, our constellations, or the shape of the Milky Way as seen from the Sun. Instead, it draws lines from one point toward 14 pulsars. Beside each line is a binary number representing the pulsar's rotational period at the time the record was launched. A 15th line points toward the center of the galaxy. Together, the pattern forms a kind of cosmic return address. The logic is elegant. Pulsars are rare enough to be distinctive. Their pulse periods differ. Their positions relative to the Sun create a recognizable geometry. A civilization capable of finding and decoding the record might identify those same pulsars, compare their present periods with the values engraved on the cover, and infer both where the spacecraft came from and roughly when it left. The address contains a location. It also contains an epoch. That second feature is what makes the map profound. The designers understood that a position without a date would eventually become ambiguous. Stars move, pulsars slow. The solar system travels through the galaxy. A map that only said where the Sun was would decay as the objects around it changed. So the pulse periods act like timestamps. Because pulsars gradually lose rotational energy, their pulses generally become slower over time. Compare the engraved period with the observed period, and the difference can provide an estimate of how much time has passed since launch. In principle, the map is self-aging. Its own inaccuracies become part of the clock. But no such address lasts forever. Some of the pulsars may become harder to observe from a future location. Timing noise may complicate the comparison. A pulsar could glitch. Galactic motion slowly alters the geometry. Over tens of thousands or millions of years. Uncertainties accumulate until the diagram becomes less like an address and more like an archaeological clue. The Golden Record does not point to an eternal home. It points to a moving solar system as it was characterized in 1977. That distinction applies to every star catalogue and every navigational model a spacecraft could carry. A catalogue is not a picture of the sky. It is a set of measurements attached to an epoch. Modern astrometry makes this explicit. A star's catalogue entry may include its position at a reference date, its proper motion across the sky, its parallax, and its radial velocity. From these values, software predicts where the star should appear at another time and from another location. The prediction is powerful because it includes motion. It is limited because every measured quantity carries uncertainty. Gaia, the European Space Agency mission, has measured the positions and motions of an immense number of stars with unprecedented precision. For navigation near the solar system, such data transforms the sky from a rough pattern into a dynamic three-dimensional model. A future interstellar spacecraft could carry a descendant of that model. It could propagate stars forward through decades. It could update distances as its changing viewpoint produces larger parallax baselines. It could refine the positions of nearby stars using its own observations. In effect, the ship could become an observatory that continuously rebuilds the map it uses. This is essential because the farther it travels, the less valid an Earth-centered sky becomes. Nearby stars shift perspective first. A star that once lay beside another in the sky separates from it. Familiar constellations distort. The Sun itself becomes one ordinary star among many, identifiable not by brightness alone but by spectrum, motion, and its geometric relationship to surrounding sources. The ship would need to preserve the connection between these changing observations and the catalogue from which it began. That connection is a chain of identity. This point of light is still that star. This pulse belongs to that pulsar. This spectrum matches the Sun. Break the chain, and the coordinate system can fracture. A navigation computer may know its mathematics perfectly and still fail if it assigns the wrong identity to the evidence. A false star match can rotate the entire inferred sky. A mistaken pulsar phase can shift the calculated position. A clock error can make several correct signals appear mutually inconsistent. The danger is not that the universe becomes unstructured. The danger is that structure must be recognized from a changing viewpoint. Humans solve identity through memory. A street may change, but a person returning after decades recognizes the curve of a road, the position of a river, the silhouette of a hill. A spacecraft has no childhood landscape. It has data associations. Those associations must survive radiation, hardware replacement, software updates, and perhaps generations of maintenance. The map cannot remain a sealed artifact. it must remain interpretable to systems that may be rebuilt long after launch. For a voyage lasting centuries, navigation becomes an institutional problem as much as a mathematical one. Future crews must understand why a catalogue was constructed, how uncertainties were represented, which sensors were trusted, which pulsars had glitched, and which stars had become unreliable references. A number without its history can become dangerous. A correction performed by one generation may look like an error to the next. A calibration constant may survive after the instrument it described has been replaced. A software patch may encode assumptions that no living engineer remembers. The spacecraft must preserve not only its position estimate, but the reasoning behind that estimate. It must carry a memory of how it knows. This is where the Golden Record becomes more than a historical artifact. Its map is simple enough to survive without software. The diagram does not depend on a database format, an operating system, or a living institution. It reduces the address to geometry, timing, and a physical inscription. Yet even this simplicity cannot escape time. The pulsars continue aging. The sun continues moving. The record itself drifts along a trajectory that will carry it far from the geometry shown on its cover. If someone finds it in the distant future, the map will not say, "This spacecraft belongs here." It will say, "This spacecraft once came from a system that was here, relative to these clocks, when they ticked at these rates." That is the most honest address the universe allows. Not a permanent coordinate, a historical relationship. For an interstellar traveller trying to return, the same principle must be reversed. The ship cannot aim for the remembered position of the solar system. It must identify the present descendants of old references, update their motion, infer its own epoch, and predict where the sun's world line will be crossed. Every usable landmark must be carried forward in time. Every clock must be interpreted. Every identity must survive. The closer the ship comes to home, the more precise that chain must become. A rough pulsar fix may guide it toward the correct region of the galaxy. Star geometry may identify the solar neighborhood. The sun's spectrum and motion may isolate it from nearby stars. Radio or laser beacons could then refine the final approach. Layer by layer, the address becomes local again. But the ship can only perform that descent if its own memory remains intact. A traveller lost in deep space is not merely someone who does not know where Earth is. It is someone who can no longer connect what the universe looks like now with what it looked like when the journey began. And that is why the next requirement is not a better map. It is a ship capable of preserving, questioning, and rebuilding its own knowledge for longer than any machine has ever remained alive. That requirement changes a spacecraft from a vehicle into an institution. It must not merely carry instruments, it must carry methods for deciding which instruments deserve trust. A star tracker may report one orientation, an inertial system may report another. A pulsar solution may place the spacecraft thousands of kilometers away from both. Somewhere inside that disagreement lies the truth, but the truth is not labelled. The ship must infer it. Modern spacecraft already perform limited versions of this task. Navigation software compares predicted measurements with actual ones, rejects obvious outliers, updates estimates, and raises alarms when residuals grow too large. An interstellar craft would need to do far more. It would need to distinguish a damaged sensor from an unexpected force. It would need to recognize when a catalogue had become outdated, when a clock had drifted, and when two independent systems agreed only because they shared the same hidden assumption. This is not ordinary automation. It is epistemology turned into machinery. The spacecraft must know what it knows, estimate how well it knows it, and notice when the foundations of that knowledge begin to fail. Imagine 3 navigation systems operating at once. The inertial system says the ship is on course. The star tracker says it is slightly rotated. The pulsar solution says the onboard clock is slow. Any one of these readings could be wrong, or all 3 could be partly right. A clock error can make pulsar pulses appear displaced. A rotation error can corrupt the identification of stars. A mistaken star match can make the inertial system appear to have drifted. The errors are coupled, so the ship cannot repair them one at a time without considering the rest. It must solve for position, velocity, orientation, clock state, sensor bias, and environmental forces together. And it must do this while moving. A mistake in diagnosis becomes a mistake in action. Suppose the navigation computer concludes that a thruster burn underperformed. It commands a correction. If the real problem was a clock offset, the correction pushes the ship away from the proper path. Fuel is spent. The original error remains. A new error has been created. Course corrections cannot be triggered by uncertainty alone. The system must weigh the cost of acting against the cost of waiting. Act too early, and the ship may chase noise. Act too late, and a real deviation may grow until correction requires far more propellant. Every burn consumes a finite resource. Propellant cannot be replenished between stars. Reaction wheels saturate. Valves wear. Engines lose performance. A spacecraft may possess enough fuel to survive a handful of major corrections, but not an endless sequence of doubtful ones. Navigation is therefore not just a problem of accuracy. It is a problem of restraint. The safest system is not the one that reacts fastest. It is the one that knows when evidence is sufficient. To make that judgment, the ship needs redundancy. But redundancy is useful only when systems fail differently. 3 identical gyroscopes may provide confidence during normal operation. Yet if all were built from the same design, exposed to the same radiation, and calibrated by the same procedure, they may drift together. Agreement can become a shared mistake. True redundancy requires different physical principles. Optical gyroscopes can be compared with cold atom sensors. Star tracking can be checked against pulsar timing. Radio ranging can be checked against optical beacons. Independent clocks can be built from different atomic transitions. The goal is not to make failure impossible. It is to make failure visible. When methods based on different laws of physics converge on the same answer, confidence rises for a meaningful reason. When they diverge, the disagreement exposes the boundary of knowledge. Deep space navigation is disciplined disagreement between imperfect instruments. But even the best sensors are useless if the ship cannot preserve the context needed to interpret them. A crew may replace a damaged camera with a newer design. The replacement will have different optical distortions, thermal behavior, and radiation response. Old calibration files may no longer apply. Software written decades earlier may assume hardware that no longer exists. The system must preserve more than raw numbers. It must preserve provenance. Which instrument produced this measurement? Under what temperature? Using which software version? After which repair? Relative to which catalogue epoch? With what uncertainty model? Without that history, a precise data point may become meaningless. A spacecraft surviving for centuries would accumulate layers of technical memory. Components would be replaced. Algorithms would be rewritten. Units might change. Human language might drift. The crew responsible for navigation could inherit systems whose original designers had been dead for generations. The machine would need documentation capable of surviving its own evolution. That sounds mundane beside relativistic travel and neutron stars. It may be one of the hardest requirements of all. Human institutions forget. File formats become unreadable. Standards disappear. Explanations are shortened and misunderstood. A calibration procedure that once seemed obvious can become ritual, repeated because it has always been repeated, long after its physical justification has been lost. In deep space, ritualized error can kill. The spacecraft must continually test whether inherited knowledge still predicts reality. A star catalogue cannot be trusted because ancestors trusted it. A sensor cannot be trusted because it passed inspection 50 years earlier. A correction rule cannot survive merely because it once worked near the sun. Everything must remain falsifiable. The ship must be capable of saying, "This model no longer explains what we observe." Then it must build a better one. That ability may require scientific instruments far beyond ordinary navigation equipment. The spacecraft may need to measure local dust density, magnetic fields, stellar spectra, gravitational influences, and radiation environments. It may need to refine the masses and motions of nearby stars as it travels. In effect, the vessel would have to conduct astronomy in order to know where it is. Its map would not be carried intact from Earth. It would be rebuilt along the way. Artificial intelligence could help manage this complexity, but intelligence does not remove uncertainty. A capable system can compare more models and detect subtler patterns. It can also produce more elaborate mistakes if its assumptions are wrong. The danger is not a machine that refuses to navigate. The danger is a machine that offers a convincing explanation for the wrong universe. So every autonomous conclusion must remain tied to evidence that can be independently checked. The ship needs internal debate. One system proposes a state estimate. Another attempts to disprove it. A third searches for observations that would distinguish competing explanations. Only then does the spacecraft decide whether to change course. This is slower than blind confidence. It is also how the ship remains alive. Earth may still send occasional updates across the years. New pulsar models, revised stellar motions, warnings about catalogue errors, perhaps a better estimate of where the solar system will be at the planned return epoch. Those messages would enter the ship not as commands, but as evidence. The onboard system would compare them with its own history. If they agreed, uncertainty would shrink. If they conflicted, the ship would decide whether Earth's model was stale, its own model had drifted, or both were wrong differently. There may be no immediate answer, only another observation, another pulse, another star field, another year of motion before the disagreement resolves. This is what independence means between stars. Not freedom from Earth, responsibility without timely rescue. And even if the ship performs that responsibility perfectly, even if it preserves its records, diagnoses its failures, updates its sky, conserves its fuel, and predicts the solar system's future position accurately, the final approach contains a truth no navigation computer can correct. The spacecraft may find Earth. The traveller may still fail to find home. The failure begins with success. After years or decades in darkness, the spacecraft identifies the sun. Its spectrum matches. Its motion agrees with prediction. Pulsar fixes. Stellar geometry and delayed signals from Earth converge on the same conclusion. The solar system is ahead. At first, nothing changes visually. The sun is still only one star among many. Then, slowly, it brightens. The planets separate from the background. Radio beacons grow stronger. The navigation solution tightens from light years to astronomical units, from astronomical units to millions of kilometers. The uncertainty cloud collapses. For the first time since departure, the word arrival becomes physical. This is the moment most stories treat as resolution. The traveller has found the correct star. Earth has been located. The remaining task seems almost ordinary. Reduce speed, enter the proper trajectory, and descend toward the planet. But the equations have solved only the astronomical problem. They have not solved the human one. The Earth ahead is not the Earth that was left behind. It is the same world line at a later event. That distinction remains invisible from a distance. The planet still reflects blue light. Clouds still cross oceans. The moon still circles. Continents preserve their recognizable outlines. From far away, continuity appears complete. Only the signals reveal the rupture. News archives arrive. Faces have aged. Voices have disappeared. Buildings once familiar have been demolished, rebuilt, or renamed. A language still spoken may have shifted in accent and meaning. Political borders may have changed. Technologies considered impossible at departure may be ordinary. The traveller did not witness the transition. History happened as an incoming data stream. This creates a form of displacement unlike ordinary exile. An exile on Earth may return after decades and find a transformed city. But both the traveller and the city have lived through roughly the same span of time. their bodies carry the same years. A relativistic traveller may return having experienced far fewer. People born after departure may be older than the returning crew. Children remembered at 5 may have grandchildren. Someone who promised to wait may have lived an entire life. Not because the journey felt equally long to both, but because space-time gave them different amounts of duration. The traveller arrives from the past without having been preserved inside it. That is what time dilation does to homecoming. It does not freeze the ship. It allows the crew to live normally, while the world they left accumulates more history than they do. No instrument aboard feels broken. No clock runs strangely. The asymmetry appears only at reunion. A hand touches another hand and finds decades between them. This is why a perfect trajectory cannot restore the meaning of return. Navigation can make two world lines intersect. It cannot make their accumulated time equal. The spacecraft may carry recordings from departure, a final meal, the sound of rain against a window, a parent speaking into a camera, a city seen from orbit. Those records preserve light and sound with extraordinary fidelity. They do not preserve the event itself. A recording can be replayed, a moment cannot. The distinction seems philosophical until the ship reaches Earth. Then it becomes operational. Which legal identity does the traveller possess? Do contracts remain valid? Does citizenship persist? Who controls the mission? Which institutions still exist to receive it? The return was planned by people who may be dead and organisations that may have dissolved. Landing facilities may have moved. Communication standards may have changed. Even the beacons guiding the ship could belong to systems built long after launch. The spacecraft has navigated toward continuity. It may encounter replacement. This does not mean the future Earth will reject the travellers. It may celebrate them. Their arrival may be one of the most anticipated events in human history. Entire generations may have followed the mission's delayed transmissions. But recognition is not restoration. The people waiting know the travellers as figures from archives. The travellers know Earth through memories of a society that no longer exists in the same form. Each side receives someone real, yet neither receives exactly the person or world imagined. The reunion contains grief, even if it is joyful. That grief is not caused by navigational error. It is caused by navigational accuracy arriving too late to save what accuracy cannot measure. An ephemeris includes position and velocity. A guidance computer may include uncertainty. A mission clock records elapsed time. None of these contains belonging. Home is not encoded in the orbit of Earth. It exists in relationships synchronized for a while. People sharing meals. Streets walked often enough to become automatic. Voices expected at certain hours. Small routines repeated until they become part of identity. Distance interrupts those synchronizations. Relativity makes the interruption unequal. By the time the traveller returns, the planet may occupy exactly the predicted coordinates, but the network of relationships that made those coordinates meaningful has evolved without them. The planet can be recovered. The life attached to it cannot be rewound. There is a harsher possibility. Suppose the voyage lasts not decades but centuries in Earth's frame. The returning spacecraft may still be operational. Its crew may have aged only modestly because of extreme velocity, suspended animation, or generations living aboard. Yet the civilization that launched it could be unrecognizable. Humanity may have spread through the solar system. Earth may no longer be the political or cultural center. New habitats may consider the old planet ancestral rather than central. The traveller's definition of home could be historically accurate and socially obsolete. The target survives. Its status changes. Or perhaps the voyage is undertaken by a generation ship, moving slowly enough that relativity is minor, but long enough for many generations to pass aboard. In that case, the problem reverses. Earth may remember the mission. The returning descendants may not remember Earth except as inherited language. They know oceans from archives. They know gravity from shipboard simulations. They know the smell of soil as chemistry, not memory. Their ancestors departed from home. They are approaching an origin. For them, the blue planet is not a lost room. It is a story, with weather, This reveals that home can drift on both sides of the journey. Earth changes. The traveller changes. Memory changes. The word remains while its object moves. By the final approach, the spacecraft may possess the most accurate navigational solution ever achieved. It may know its position to meters. It may synchronize with orbital traffic, match velocity with Earth, and descend through the atmosphere along a corridor calculated decades earlier. The sky brightens. Air strikes the hull. Gravity returns as weight. The hatch opens. Every physical instrument reports success. The traveller has reached Earth. Whether the traveller has reached home can no longer be decided by physics. And if the journey has lasted long enough, even the person asking the question may no longer mean what the person who departed once meant. Meaning is not stored in coordinates. It is stored in continuity. A place becomes home because the mind links one experience to the next. The same doorway is crossed hundreds of times. The same voices answer. The same weather returns. Familiarity is not a single memory, but a chain of recognition stretched across years. Break the chain long enough, and the place may remain, while the meaning thins. For a traveller who leaves Earth and returns after a few years, that chain can survive. For a traveller separated by decades, the connection becomes fragile. For a crew living across generations, it becomes an inherited construction. The first generation remembers the launch site. The second remembers stories about it. The third remembers the stories as tradition. By the fourth, Earth may no longer be a remembered world. It may be a sacred origin, a political symbol, a disputed history, or simply one destination among others. The coordinates remain exact. The reason for returning changes. This is not a failure of loyalty. It is what cultures do. Language shifts. Rituals gather new meanings. A song carried from Earth may still be sung aboard the ship, but its pronunciation changes and its emotional center moves toward the life of the vessel. The ship develops its own calendar, its own anniversaries, its own places of mourning. A corridor where an accident occurred becomes significant. A garden module becomes the nearest thing to a forest. The engine's vibration becomes so familiar that silence feels unnatural. Children learn the names of oceans before they understand what an ocean physically is. They may know Earth in greater detail than many people who once lived there. Every continent can be studied. Every city can be reconstructed in simulation. Archived voices can speak with perfect clarity. Yet knowledge does not create memory. A person can memorize the spectrum of sunlight filtered through Earth's atmosphere and still never have stood beneath a blue sky. For the descendants of an interstellar crew, returning to Earth would not be a homecoming in the ordinary sense. It would be an encounter with the place their ancestors used to mean when they said home. That difference affects navigation more than it first appears. A mission survives through decisions. Fuel is allocated. Repairs are prioritized. Risks are accepted. A return trajectory may require decades of preparation and sacrifice. The people making those choices need a reason strong enough to justify them. If Earth has become abstract, the original mission objective can lose force. Why spend irreplaceable propellant to return to a planet no living crew member has seen? Why accept the danger of deceleration and solar system entry when the ship contains every known relationship and every familiar room? At some point, the vessel may become more home than the destination. Then the hardest navigational decision is not how to return. It is whether the word return still describes what anyone wants. This creates a quiet reversal. The spacecraft was built as the thing that left home. Over generations, it can become the stable reference around which all other meaning is organized. Earth, once the fixed origin, becomes the moving object far away. The ship's children wake in the same compartments. They know which handhold comes before return. They recognize changes in the air system by sound. They can move through darkness without thinking. Relative to their lives, the vessel is still. Earth is the wandering light. That is how every home works. It appears fixed because the people inside it share its motion.
The original illusion returns at a smaller scale.
A spacecraft crossing the galaxy can feel motionless to those born aboard it, just as Earth feels motionless to those born on its surface. The body does not experience constant velocity. Culture does not feel its own drift. Both are detected only by comparison with something outside. But the farther the ship travels, the weaker that comparison becomes. Messages from Earth arrive after years. Replies describe people who may be dead by the time the crew hears their voices. Cultural changes appear without transition, as fragments from a history unfolding elsewhere. A language can transform between transmissions. A government can disappear between one message and the next. The crew receives consequences without living through causes. This makes Earth difficult to interpret even when communication survives. A message may use words whose meanings have changed. A symbol once associated with one institution may belong to another. Instructions may assume technologies or social structures the ship does not possess. The two populations remain biologically human while becoming historically remote. Translation becomes necessary within the same species. The gap runs both ways. Earth receives reports from the ship, separated by years, each describing a society that has already changed before the transmission arrives. Mission planners cannot guide a culture they observe only in delayed fragments. Both sides communicate with ghosts, not dead people, necessarily, but expired versions of living communities. The Earth that hears the ship is not the Earth the ship addressed. The ship that receives the answer is not the ship that asked. This is the human form of light-speed delay. Physics turns every long-distance conversation into archaeology. A command sent from Earth may arrive after the authority that issued it has lost legitimacy aboard the vessel. A promise made by the ship may reach Earth after the crew has changed its plans. What began as one mission can divide into competing understandings of obligation. The navigation computer may still know the route. The society carrying it may no longer agree on the destination. A coordinate can survive longer than the reason anyone wanted to reach it. This is especially dangerous because purpose affects maintenance. Someone must keep calibrating the instruments, preserving the pulsar records, verifying the clocks, and teaching the next generation why those tasks matter. If the meaning of return fades, the technical ability to return may fade with it. A catalogue is neglected. A backup detector is used for another purpose. A maneuvering reserve is spent to solve an immediate crisis. None of these decisions is irrational. A society inside a closed spacecraft must prioritize survival in the present over the intentions of ancestors. Over centuries, the route home can be lost, not through one catastrophic error, but through 1,000 reasonable choices. This is another way certainty leaks away. Not from instruments, from culture. A machine can preserve data, but only a living community can preserve the importance of that data. No archive explains itself forever. Every map needs a reader. Every destination exists inside a story about why reaching it matters. The story can drift farther than the ship, and yet the desire to return may survive in forms no mission planner predicted. Earth may become mythologized. Generations who have never felt rain may dream of it with an intensity no one on Earth understands. Then the return is no longer toward memory. It is toward an invention. The blue world becomes a promise constructed from absence. When it finally appears ahead, real and clouded and physically ordinary, the travellers may discover that no planet could equal the home built inside centuries of longing. The equations will still be correct. The disappointment will be human. Too many things have moved. Earth, the spacecraft, the clocks, the cultures, the language, and the person asking to go back. By then, home is not one coordinate waiting to be recovered. It is several incompatible places layered over the same planet. The remembered Earth, the inherited Earth, the present Earth, the Earth that will exist when the ship arrives. Navigation can choose only one of them, and only one is physically reachable. The reachable Earth is the one that lies ahead. Not ahead in the simple sense of direction, ahead in time, A returning spacecraft cannot point toward the light it currently sees and expect to arrive where that light came from. The photons entering its instruments left the solar system years earlier. They show the sun and planets at positions already abandoned. The ship must aim somewhere else. It must predict the future. Long before the sun becomes bright enough to dominate the sky, the navigation system begins constructing an intercept. Pulsar timing narrows the spacecraft's galactic position. Stellar spectra identify the solar neighborhood. The motions of nearby stars reveal whether the onboard catalogue has remained aligned with reality. Then the sun is isolated, not as the brightest point, but as a specific star with a known spectrum, mass, motion, and family of orbiting worlds. The ship does not steer toward the sun's observed image. It computes where the solar system will be when the remaining distance is crossed. This is the same logic used for every planetary mission, extended across a far more severe scale. Spacecraft never fly toward where Mars appears in the sky. They aim toward the point where Mars and the spacecraft are predicted to arrive together. Interstellar return is an intercept problem too, but the target is no longer one planet moving around one star. It is a layered system. The Sun moves relative to neighboring stars. Earth orbits the Sun. The Moon perturbs Earth. Other planets shift the solar system barycenter. The spacecraft approaches with a velocity that may be enormous compared with anything humanity has yet attempted to slow. Reaching the correct region is not enough. The craft must arrive with the correct velocity. A ship that crosses Earth's orbit at a meaningful fraction of light speed has not come home. It has passed through the solar system in minutes, carrying enough kinetic energy to make capture impossible without a method of extreme deceleration. Navigation therefore includes braking from the beginning. Every acceleration during departure creates a future obligation. The faster the outbound journey, the more energy must eventually be removed. The trajectory home is shaped not only by where Earth will be, but by how the ship can shed speed without exhausting fuel, destroying itself, or missing the narrow geometry of capture. A destination is not a point. It is a point, a time, and a velocity. Miss any one of the three, and the encounter fails. This is why a rendezvous between two spacecraft is harder than one craft reaching a planet. Two moving objects must arrive at the same place simultaneously with compatible velocities. Otherwise, they merely cross. Earth is easier to predict than a damaged spacecraft because its orbit is stable and observed continuously. But the returning ship carries the larger uncertainty. Its route has been altered by decades of sensor drift, maintenance, corrections, and unmeasured forces. The final approach becomes a contest between shrinking distance and remaining doubt. Signals from the solar system grow stronger. What once required days of integration can be detected in hours, then minutes. Artificial beacons become distinguishable from natural radio sources. The ship receives updated ephemerides that are no longer years old by the time they arrive, but months, then days. The control loop begins to close again. For the first time in generations, Earth can respond to a problem before the spacecraft has moved unimaginably far beyond the state being discussed. Yet this return of guidance creates another risk. The ship has survived by trusting its own models. Earth has built newer models, newer instruments, perhaps an entirely different navigational language. Their estimates may disagree. Which one should lead? The planet has better knowledge of the present solar system. The ship has better knowledge of its own hidden history. Earth may know where the receiving corridor should be. The spacecraft knows which thrusters have aged, which sensors were replaced, which structural stresses changed its response, and which apparent anomalies were never fully explained. Neither side possesses the whole truth. The final navigation solution must be negotiated between them. A message from Earth recommends a burn. The ship simulates it through every surviving model. One system predicts safe capture. Another predicts a miss. A third warns that the engine response assumed by Earth has not been valid for 30 years. There is no time for an 8-year exchange now. The distance has narrowed. Decisions accelerate. The returning vessel must combine the authority of home with the evidence of its own survival. This is the last technical form of the problem that began at departure. No observer has a complete view. Knowledge remains local. Earth knows Earth. The ship knows the ship. The rendezvous exists only if both descriptions can be made consistent. Eventually, the uncertainty becomes smaller than the target corridor. A burn begins. The engines that once carried the spacecraft away now fire against its motion. The cabin vibrates. Stored energy becomes heat. Velocity falls. The sun remains ahead longer with each passing hour. At last, the ship is no longer crossing the solar system. It is entering it. The difference may not be visible from the cabin, but mathematically, it is decisive. The spacecraft's trajectory has become bound or capture compatible rather than a fleeting hyperbolic passage. The solar system is no longer something the ship will leave behind again automatically. For the first time, home has gravity. Then Earth appears as more than a calculated object. A pale point becomes a crescent. The crescent grows. Weather systems emerge. The night side reveals artificial light arranged in patterns the travelers do not recognize. The planet is visually familiar and historically strange. Every instrument confirms identity. Atmospheric spectra match. The Moon occupies the predicted orbit. Radio traffic fills frequencies once empty. The coordinate has been recovered. But the word home remains unresolved because the final coordinate is not astronomical. It is the relationship between the traveler and the world ahead. Physics can determine whether the spacecraft reaches Earth. It cannot determine whether the returning crew still belongs to the civilization receiving it. No sensor measures that distance. No burn removes it. The travelers may understand every word transmitted from the planet and still hear an accent shaped by years they never lived. They may recognize the continents and fail to recognize the society. They may be welcomed by descendants of people whose final messages are still stored aboard the ship. The last human coordinate is continuity. Where do you belong in a history that continued without you? Where does a society place someone who left its past and arrives in its future? The equations cannot answer. They end at the atmosphere. Everything beyond that point belongs to memory, identity, and grief. This is why the final approach is not merely the solution to navigation, it is the moment navigation reveals its limit. The ship has crossed interstellar darkness using clocks, stars, pulses, models, and doubt. It has done what once seemed impossible. It has found the correct moving planet at the correct future time. And still, as Earth fills the window, the travellers face the question that no map could preserve for them. Not where they are, who they are now that they have returned. Who they are now that they have returned cannot be solved by the same instruments that brought them there. The ship can measure velocity relative to Earth. It can synchronize clocks. It can compare the planet's present atmosphere with records made before departure. It can prove, beyond doubt, that this is the same world. But sameness in physics is not sameness in experience. The spacecraft enters orbit, below. Oceans turn beneath bands of cloud. Storms rotate in familiar shapes. Sunlight moves across the curve of the planet exactly as it did in old recordings. From this height, Earth appears almost untouched by time. That appearance lasts until the details arrive. Coastlines have shifted where rivers changed course and seas advanced. Cities spread into patterns no one aboard recognizes. Some places remembered as bright are dark. Other regions glow across entire nights. The launch complex may be preserved as a monument, buried beneath later construction, or gone. The crew can locate the coordinates of every remembered place. Coordinates cannot tell them what survived there. A landing site is chosen. The spacecraft leaves orbit and begins descending through an atmosphere it has not touched for years. Friction gathers around the hull as light. Plasma blocks communication for a few minutes. Gravity, absent or simulated for most of the journey, becomes a force the body can no longer ignore. The planet presses upward through the seat. Air thickens. Cloud surrounds the windows. Then the ship falls beneath it. For the first time since departure, the travellers see a horizon that belongs to a nearby world. The sky has a direction again. Down is no longer a convention painted on a cabin wall. Mountains hold still against the distance. The surface approaches. Every human instinct says they are coming back. The mathematics says only that they are arriving. That difference has followed them across the entire journey. When the engines stop, silence does not feel like the silence between stars. Wind moves against the hull. Rain may strike metal. Somewhere beyond the landing area, water runs. Leaves move. Insects call. And human voices speak without crossing an antenna first. The hatch opens. Nothing in deep space prepared the body for smell. Soil, moisture, plants, machines. The dense chemistry of a living planet enters all at once. Air has weight. Temperature touches the skin unevenly. A breeze arrives from one direction and proves that direction exists. The travellers step down. Perhaps the first face they see belongs to someone who studied their mission as ancient history. Perhaps the person knows the names of the crew, the date of departure, and every public message they sent. To the person waiting, the travellers are legendary. To the travellers, the person is a stranger standing on familiar ground. This is the final asymmetry. Earth has had years to imagine their return. They have had memories with which to imagine Earth. Neither imagination is the thing now present. There may be ceremonies. There may be embraces. There may be medical teams, cameras, descendants, officials, and crowds repeating words that once carried uncomplicated meaning. Welcome home. The phrase will be sincere. It will also be incomplete. Home was never merely the planet. It was a temporary alignment between a place, a time, and a life. The alignment held because all three moved together. The traveller left that shared motion. Earth continued along its world line. The ship followed another. Now those lines meet again. The intersection is real. The continuity is not. This does not make the return meaningless. A future can be built from reunion. New relationships can begin. The traveller can learn the changed world. The planet can become home again, slowly, through repetition rather than recovery. A road can become familiar. A voice can become expected. A room can gather memory. But this would be a new home assembled at the destination, not the old one waiting intact. The distinction is not pessimism. It is the honest price of distance. Every journey changes the traveller and the place left behind. Deep space only extends the separation until the change can no longer be ignored. It strips away the comforting assumption that home is an object preserved by absence. Nothing is preserved by absence. Not people, not societies, not stars, not the traveller. The universe is not a warehouse of fixed locations. It is a structure of events, each occurring once, each connected to others by paths that move only forward through time. A spacecraft can calculate those paths. It can bend its own with engines. It can use dead stars as clocks, distant quasars as reference points, and signals from Earth as delayed evidence. It can reduce uncertainty until the solar system is no longer a prediction, but a visible place ahead. That achievement would be extraordinary. It would not reverse anything. This is why the word back is dangerous. It hides two different desires inside one direction. The first is physical, return to Earth. The second is impossible. Restore the world as it was when you left. Physics may eventually grant the first, better clocks, autonomous navigation, pulsar timing, laser beacons, and instruments not yet built could guide a ship across interstellar space and bring it to the correct planet. No instrument can grant the second. The morning of departure is not waiting at a coordinate. The last conversation has not remained suspended in the room where it ended. The people who waved from the ground were not held still by the traveller's memory. Those events exist in the history of space-time. They do not exist as destinations. A ship may travel close to the speed of light. It may cross years of distance while its crew experiences far less time than Earth. It may return with every navigational calculation correct. But no speed shortens the past into reach. No course points toward yesterday. The most precise map humanity could ever create would still contain only future meetings. And so the traveller looking through the window during the final approach would understand something that could not have been understood at launch. The darkness was never the deepest obstacle. The stars were never truly the problem. The problem was the assumption that home would remain on the far side of the journey, unchanged, patient, and available for recovery. It did not remain. It lived. It aged. It became something else. So did the traveller. Deep space does not erase the road home. It reveals that the road was never pointing backward. You may cross the darkness and find Earth exactly where the equations said it would be. You may see the blue of its oceans, feel its gravity take hold, and hear another human voice without delay. You may recover the planet, but the home you remember will not be waiting there. It was not lost in space. It was lost in time.